In this chapter, we are considering the Curvy linear coordinate system to describe the Newtonian mechanics in terms of the Lagrangian mechanics. Last class, we have found a way to describe the Lagrangian mechanics in terms of Curvy linear coordinate system. In the Curvy linear coordinate system, Q1, Q2, Q3 must be able to describe all three Cartesian components, x1, x2, and x3. So first of all, we evaluated this delta L variation of the Lagrangian in terms of the three Cartesian coordinates. And then we developed a way to redescribe this variation in terms of the Curvy linear coordinate system's variations. The computation was quite involved, but at the end of the stage, we found a very compact form, and actually it is very trivial to obtain directly from the original derivation in terms of the Cartesian coordinates. It is nothing but a simple replacement of xi's with the qi's and qi dots. So this Curvy linear coordinate system counterpart is equivalent to the variation of the Lagrangian in the Cartesian coordinate system. As a result, variation of the action was carried out in the Curvy linear coordinates, and the surface term contains the variation of endpoints, and variation of the endpoints vanishes, just like the case of the Cartesian coordinates, qi, qi. For I equals 1, 2, and 3. So in order to have this action to be minimized or extremized along the physical path under the variation of every generalized coordinates qi independently, we must have the coefficient of every dq delta q k to be 0 exactly. That is the Euler-Lagrange equation in the generalized coordinate system. So as a result, if the least action principle still holds in the generalized coordinates, then the integrand must vanish for any variation for any generalized coordinate that are varied independently. Therefore, the Euler-Lagrange equation should be true for generalized coordinates. So, equipped with this strategy, we can attack any problem in the generalized coordinates, especially in the Curvy linear coordinates. And here we consider mainly the cylindrical coordinate system and the spherical polar coordinate system. Okay. Any set of quantities qi that can describe the state of mechanical system completely is called the generalized coordinates. Until now, we mainly studied the Cartesian coordinates that are all orthogonal to among one another, and the basis vector along the x1, x2, x3 axes are all orthogonal and all constant. And there is a translation invariance of those basis vectors. Just like what we did for the derivation of momentum from the Lagrangian, in the Cartesian coordinates, if I take the derivative of the Lagrangian with respect to the velocity along the Cartesian axis xi, then we obtain the linear momentum mxi dot. That is called the conjugate momentum. Just like the case of the Cartesian coordinate system, we have the generalized momentum or the conjugate momentum pi corresponding to each generalized coordinate qi. That can be obtained by taking the partial derivative of the Lagrangian with respect to qi dot. That's simple. The resultant Euler-Lagrange equation contains the time derivative of this generalized momentum equals a Lagrangian's partial derivative with respect to the generalized coordinate qi. In the case of the cylindrical coordinate system, the Lagrangian should be written in those coordinates. The potential energy was a function of x1, x2, and x3. As we know, all three Cartesian components are expressed in terms of Curvy linear coordinates q1, q2, and q3. If we introduce the generalized coordinates to describe the Lagrangian, we also need to express the kinetic energy. It was expressed in terms of 1/2 mxi dot squared in the Cartesian coordinate system. If we rewrite this one in the generalized coordinates such as the cylindrical coordinate system, it is composed of velocity squared along the rho direction. The velocity squared is the time derivative of rho squared. The velocity along the phi direction contains the scale vector rho. So rho phi dot is the velocity along the phi direction. So the velocity square is the rho square phi dot square. The velocity along the z direction is a z dot. Thus the v square along the z direction should be z dot squared. As you can see, the direction along the planar radial direction rho and along the direction of z along these two directions, there is no change in the overall vector. It is just coordinate dot square is the velocity square. However, if the generalized coordinate is an angle, phi is an azimuthal angle, and velocity is dimension of length divided by time. So in order to have the dimension of length and in order to match it with the actual arc length, we have to multiply the scale vector rho to obtain the velocity along that angle. That means that velocity along the phi direction is rho times phi dot. All right. So in these two cases, the generalized momentum or conjugate momentum corresponding to the coordinates representing length, this is just the linear momentum. It's m times rho dot, m times z dot. However, if we consider the generalized momentum corresponding to the angle variable, this is an angle. If I take the derivative with respect to the angle, time derivative, the angle, we have additional factor rho squared that is a scale factor squared. Therefore, this differentiation decreases the power of velocity square to have a velocity, the time derivative of this generalized coordinates. We end up with the mass times rho square times time derivative of angle phi theta. Actually, this rho is a lever arm for the rotation about the z-axis. Rotation about the z-axis with the phi dot angular velocity involves radius of rho as a lever arm. If something of mass m is rotating with the angular velocity phi dot with the lever arm, there's the perpendicular distance of rho square. If it rotates, the angular momentum, linear momentum is m rho phi dot. This is a linear momentum, and this is the lever arm, and this is these two are making right angles. So radius times lever arm times linear momentum, that is r cross p. Therefore, r cross p is r cross p equals m rho square phi dot, and along this direction z hat. This is actually phi dot's generalized momentum corresponding to the generalized coordinate phi is angular momentum instead of linear momentum. In summary, we look into this Lagrangian in the Cartesian coordinates and Lagrangian in the generalized coordinates. The corresponding for each coordinate, we have generalized momentum or conjugate momentum corresponding to this coordinate. That is obtained by taking the derivative, partial derivative with respect to the time derivative of that coordinate of the Lagrangian. In the case of generalized coordinate, the same thing is carried out, and corresponding generalized momentum is obtained by taking the partial derivative of the Lagrangian with respect to the time derivative of the generalized coordinate Qi. If we compute the generalized coordinate, we take the Lagrangian's partial derivative, and Lagrangian is actually the kinetic energy minus potential energy, because we do not consider the velocity dependent potential. The partial derivative of the potential energy with respect to the Qi dot must vanish. Therefore, this partial derivative is equivalent to the partial derivative of the kinetic energy with respect to the Qi dot. If we consider the cylindrical coordinates, the P rho, P phi, Pz can be obtained by taking the partial derivative of the kinetic energy, because the U is independent of the rho dot, phi dot, and z dot. So we just collect the rho dot dependent kinetic energy, phi dot dependent kinetic energy, and z dot dependent kinetic energy in here. The rho dot dependent kinetic energy is here. This is the kinetic energy, right? So rho dot dependent kinetic energy is 1/2 m rho dot square. If I take the rho dot derivative, it is just m rho dot. The phi dot dependent kinetic energy is 1/2 m rho square phi dot squared, and the result is m rho square phi dot. The z dot dependent kinetic energy is 1/2 mz dot squared, and the partial derivative with respect to z dot is mz dot. As we can see, mass is multiplied, and in the case of the scale factor h equals 1, it does not have additional factor, and we only have coordinate time derivative factor. So mass times velocity is the coordinate time derivative, but because the rho dot itself is the velocity along that direction. In the case of phi, hi is a length. That is, hi is, in this case, hi is, h rho is rho. Thus, the kinetic energy is rho square factor. And this rho square factor remains the same in the final stage because the phi dot, the velocity was rho phi dot, but velocity squared in the kinetic energy has rho square phi dot squared. The derivative with respect to the phi dot decreases the power of rho dot phi dot squared by 1. However, this over factor rho dot does not change. Therefore, the lever arm squared remains. Therefore, for any coordinates involving the angle, the scale factor hi should be length, and generalized momentum has mass scale factor squared multiplied by the time derivative of the angle. That means orbital angular momentum. Especially p phi is the orbital angular momentum about the z direction. Now, let us consider the case of the Lagrangian described in the spherical polar coordinate system. In the spherical polar coordinate system, the kinetic energy is written in this form, 1/2 m times the velocity squared. And, radial direction velocity is r dot, and theta direction velocity is r theta dot, and phi direction velocity is r phi dot sine theta. We know that this r is the lever arm, and r sine theta is the lever arm of this rotation. The potential energy is described in terms of the Cartesian coordinates, and then if we introduce the Curvy linear coordinate system, r theta phi, all three components are expressed in terms of q1, q2, and q3. Therefore, the conjugate momentum corresponding to r theta and phi can be computed in this manner. In the spherical coordinates, radial direction conjugate momentum is obtained by taking the partial derivative of the Lagrangian with respect to r dot. And actually, this Lagrangian potential, we do not consider potential that depends on the velocity. So the partial derivative with respect to r dot, theta dot, and phi dot for the potential energy vanish. So we do not consider that contribution. And R dot dependent contribution only appears in the kinetic energy, and the R dot dependent kinetic energy is 1/2 mr dot squared. Partial derivative of this with respect to R dot is simply obtained by mr dot, and that is the linear momentum along the radial direction. P theta, which is the orbital angular momentum, that can be obtained by taking the partial derivative of the Lagrangian with respect to theta dot. The theta dot dependent kinetic energy is written in this way, 1/2 mr squared theta dot squared. If I take the partial derivative with respect to theta dot, we obtain mr squared theta dot. Here again, we have a scale factor r, and generalized momentum corresponding to the coordinate theta has the lever arm squared. It's mr squared theta dot, and mr squared is the moment of inertia for this rotation, and theta dot is angular velocity. P phi is the generalized momentum corresponding conjugate to the generalized coordinate phi. Round L over round phi dot can be obtained by taking the phi dot derivative for the phi dot dependent kinetic energy. Phi dot dependent kinetic energy 1/2 mr squared, phi dot squared sine theta squared. The result is mr squared phi dot and sine squared. Again, our lever arm is r sine theta, so lever arm squared is included, multiplied to the mass to generate the moment of inertia about the z-axis, and multiplied by this angular velocity phi dot. In this figure, we summarize this. This is x-axis, y-axis, and z-axis. And radius, this is the position of a particle m. This is a radius, and radial direction, we have a radial direction, angular direction, this is depending on theta, and theta direction is a plane. The theta direction is actually the plane of a phi equals some number, fixed. Phi's value is fixed, and we have this plane. And the normal vector that is on the xy plane is in here, and this is the rotation, and lever arm is the radius r, because this one is this particle follows the circle if we keep the radius, both the radius and phi the same. Therefore, this is the lever arm, and r times the velocity is r theta dot, and mr theta dot, this is a momentum, tangential momentum, and this is a radius, r cross p, that is mr squared theta dot. Okay, because everything is perpendicular, we do not put any vector notation, but actually this is the direction of r cross p for the theta rotation. And the rotation about the angle phi is about actually the z-axis. Phi rotating plane is just xy plane, and this z-axis, the lever arm is, this is r, and lever arm is r sine theta. Therefore, the mass times this direction, velocity, mass times velocity, r phi dot sine theta, and this is the velocity, and this is the lever arm, r sine theta. So this one times this one, r equals p equals m r squared phi dot sine squared theta. So this one behaves as a moment of inertia, and this one behaves as omega I omega. This one behaves like the moment of inertia, and phi dot behaves omega. So I omega, that is orbital angular momentum. Okay. The spherical polar coordinates. We just studied the spherical, how to describe the conjugate momentum in the spherical coordinates and in the cylindrical coordinates. The Lagrangian of a point particle under central force is described in this way. First, the Lagrangian 1/2 mv squared status and r dot squared, r squared theta dot squared, plus phi squared, r squared phi dot squared, sine squared theta. And central force depends only on the radius magnitude of the position vector. And we have three Euler-Lagrange equations. They are like this. Round L over R minus time derivative of conjugate momentum for coordinate R. Round L over R theta minus time derivative of conjugate momentum corresponding to the angle theta. Round L over round phi minus time derivative of the conjugate momentum corresponding to the angle phi. What we just have obtained is the generalized momentum conjugate to the radius r is mr dot, that is the linear momentum. The generalized momentum conjugate to the angle theta is the mr squared, the theta dot, and r is the scale factor for the angle theta, and actually mr squared is the momentum of inertia for the rotation for the angle theta. And the generalized momentum corresponding to the generalized coordinate phi is mr squared phi dot sine squared theta. Again, r sine theta is the scale factor for the coordinate phi, and that is the lever arm for the rotation about the z-axis. If the scale factor is 1, just like the case of the radius or coordinate, this momentum, this generalized momentum, must be the linear momentum. If the generalized momentum represents the angle, the generalized momentum p theta and p phi are both angular momentum. Angular momentum is expressed in terms of the momentum of inertia and angular velocity. And momentum of inertia is mass times the lever arm squared. So the scale factor for theta equals r, so the momentum of inertia was mr squared. And its angular velocity is the time derivative of the coordinate, the theta dot. In the case of phi, the lever arm is r sine theta, which is the scale factor for the coordinate phi. Thus, the momentum of inertia is mr squared sine squared theta, and its angular velocity is phi dot. Let us look into the structure of the Euler-Lagrange equation expressed in terms of this spherical polar coordinates. in this coordinate, first of all, we can consider the radial part. In the radial part, the left-hand side, let us move to the right-hand side and consider this one only. And this one is the partial derivative with respect to r. In the case of Cartesian coordinates, the partial derivative of a coordinate for the Lagrangian is only for the potential energy, because the kinetic energy depends only on the velocity. And the time derivative of x1 squared, time derivative of x2 squared, time derivative of x3 squared. However, in the case of generalized coordinates, we have a scale factor. Scale factor has a dimension of length, and anything of a dimension of length that has the other coordinates. For example, this angle theta, in order to describe the length or velocity, it must bring in a scale factor that is depending on the radius r. This phi, in order to have this velocity scale of length scale, it must bring in the scale factor of r sine theta. Because of this, r derivative appears in the kinetic energy piece for the along the theta direction and along the phi direction. And even the theta dependence appears in the phi direction kinetic energy. That is the complication in comparison with the Cartesian coordinate system. If we consider this Lagrangian's partial derivative with respect to radius has the kinetic energy for the theta and phi direction should be considered. And this one, if I take the derivative, I have mr omega square style. This is the omega square for the theta rotation. This is the omega square for the phi rotation. For pure phi rotation, we have a phi dot squared, and then we have additional projection vector sine squared theta. Anyway, this is a kind of mr omega squared. We remember mr omega squared is the centrifugal force. Actually, this is not a force, but along the radial direction, it looks just like a force. Let us look into the case of free particle moving along a straight line with constant velocity. In the spherical polar coordinates, its radius changes. Even though there is no force at all, it experiences acceleration in the radius. So actually that is not a force. The actual force is only this one, this coming from the potential energy. So force-like contribution coming from the coordinate system structure is called fictitious force or inertial force. This is a centrifugal force. All right. And next step, we consider the equation of motion for the generalized coordinate theta. If we consider the theta contribution, we notice that theta dependence appears in the kinetic energy. Phi direction kinetic energy has the theta dependence, but central force potential does not have any contribution. For the theta dependent contribution. All right. Thus, Lagrangian's partial derivative with respect to the angle theta is obtained by taking this derivative. If I take the derivative, remaining piece will be the same, but sine squared theta becomes a sine theta, 2 times sine theta cosine theta. At the last stage, we consider the phi dependent equation. As we know, there is no explicit phi dependence everywhere. Therefore, phi derivative vanishes absolutely. There's no explicit phi dependence in Lagrangian. So phi is a cyclic coordinate, and momentum, the generalized momentum along the phi direction must be conserved. Thus, we consider this. The Euler-Lagrange equation for the radial part, this radial part, is time derivative of conjugate momentum PR equals Lagrangian's partial derivative with respect to R. And second one, time derivative of conjugate momentum P theta equals Lagrangian's partial derivative with respect to theta. And third one, this is P phi, generalized momentum corresponding to the angle phi. So time derivative is the Lagrangian's phi partial derivative. Okay. First, the radial equation. We obtained PR equals mr dot. PR equals mr dot. Okay. And then this one was obtained in here. Right? Round L over round R was obtained in here. So if I consider this, substitute in here, I have this one. Now, we take the time derivative of the generalized momentum corresponding to the coordinate R is mr double dot. Mr double dot minus mr, this one, and gradient contribution. So if there is no potential at all, mr dot has non-vanishing contribution. So even though there is no force at all, radial acceleration exists. Radial acceleration is a fictitious acceleration that is not related to the force. This is related to coordinate system. So this part is considered to be the fictitious force. P theta's time derivative is P theta. Where is P theta? P theta is here. Orbital angular momentum regarding the rotation of angle theta. That is I omega. Omega is replaced with the theta, and R is the lever arm of that rotation. So mr squared is moment of inertia for the rotation, phi rotation. So time derivative of this is, let us first take the derivative for the angular velocity, then we obtain angular acceleration. I alpha, this is torque generated by the angular acceleration. And we have 2mr dot theta dot. If I take the derivative, this one becomes 2r, and take the time derivative for r, as we have 2mr dot theta dot. This one is, if I multiply r theta dot, is velocity. Velocity time and velocity and omega, they are perpendicular to each other. This velocity times omega, v omega, 2 times v omega, that is related to the Coriolis force. This because of the rotation, it sometimes feels, actually it's not a force, but it feels like a force. This is another fictitious force. So mr squared theta double dot plus the 2mr dot theta dot minus, this is the theta derivative of the Lagrangian. Theta derivative of Lagrangian was can be found in here as mr squared by the squared sine theta cosine theta. Okay. So if I substitute everything in here, we have the equation of motion for the theta direction. And then we have a phi dependent equation. Phi dependent equation is, we found that the phi is a cyclic coordinate. So time of the phi partial derivative of Lagrangian vanishes. So this guy is a conserved quantity. As a last step, we study the central force in some more detail with the 2D polar coordinate system. You must be familiar with the Kepler's law from high school. But we remember area velocity conservation law. Area velocity conservation law is the second law of Kepler. And that is exactly same as the angular momentum conservation of the central force. We proved that any central force is applied, the system's orbital angular momentum must be conserved. If the system's orbital angular momentum is conserved, then the radius and momentum are on the plane perpendicular to the angular momentum. You know, L equals x cross p, and this is fixed, and this x and p are perpendicular to L. Therefore, as far as L is fixed in both the magnitude and direction, x and p must be on a single plane. Therefore, we can make use of 2D polar coordinate system. All of the motion happens in a single plane. So Lagrangian can be written in this way: 1/2 m times velocity squared. Velocity squared in the two-dimensional polar coordinate system is r dot squared plus r squared theta dot squared. The conjugate momentum PR can be computed as mr dot, and the conjugate momentum, that is the orbital angular momentum corresponding to theta, is obtained by this angular momentum mr squared theta dot. We remember that the partial derivative with respect to r for this Lagrangian has the force contribution, actual real force coming from the potential energy, and the coordinate dependent contribution coming from the scale vector. This one was mr theta dot squared, mr omega squared. That is a centrifugal force contribution. As far as the p theta is concerned, if I take the derivative with respect to theta in this 2D polar coordinate system, it is cyclic. Just like phi is a cyclic in the 3D dimensional polar coordinate system. Alright, so we construct the Euler-Lagrange equation for this system. The Euler-Lagrange equation for theta and r are given in here. As we know, the theta is a cyclic coordinate. The conjugate momentum, that is orbital angular momentum on that plane, is conserved, is constant. And we also have information r dot is PR over m, remember. The radial equation is PR mr dot's time derivative equals to this one. That's fine. And this p theta is constant. We can replace theta dot in terms of p theta over mr squared, where p theta is the orbital angular momentum that is constant. The radial equation is now expressed in this form. This is just like one-dimensional equation, single variable equation. So this is completely solvable. And p theta is a constant of motion. Wait a second. We can make another approach. Recall that p theta, this orbital angular momentum, is conserved in this system because theta is the cyclic coordinate. And recall also that this Lagrangian does not have any explicit time dependence. So partial derivative of this Lagrangian is completely vanishing. Recall that if it is the case, we always make use of the second form of Euler-Lagrange equation, that is the Hamiltonian. So total time derivative of Hamiltonian is minus partial time derivative of the Lagrangian. We make use of this in here. And this Hamiltonian is time derivative coordinate multiplied with conjugate momentum summed over all coordinates, subtracted by Lagrangian. We substitute PR is mr dot, p theta, mr squared, theta dot. So substitute in here and substitute the Lagrangian in here, end up with the cancellation by half, and this is the kinetic energy plus potential energy form. As I told you, the Hamiltonian must be expressed in terms of coordinate and momentum, conjugate momentum. So conjugate momentum is used. R dot, we say that R dot equals PR over M, and theta dot equals P theta over MR squared. I can substitute to find out the Hamiltonian of the system. Actually, from the second form of Euler-Lagrange equation, this Hamiltonian is another constant of motion in here. P theta is a constant motion, and Hamiltonian is also constant motion. Thus, it can be reduced into a single variable form. So this is, let us assume it is just collapse the angle into in here. We can solve this one equation as a just one-dimensional reduction. So this rotational kinetic energy contribution can be treated as additional potential energy, even if it is not a potential energy at all. It is just kinetic energy of rotation. In the sense of a one-dimensional problem, I can insert in here as a potential. So let me call this effective potential this rotational kinetic energy, plus potential energy. If I make use of this, effective potential can be, we can make a derivative of effective potential to find the effective force. That contribution is the potential energy contribution. And next contribution is coming from the rotational kinetic energy contribution. That gives plus p theta squared over mr cubed. That is exactly the same as what we obtained from the Lagrangian Euler-Lagrangian equation. So this is a combination of Lagrangian mechanics and Hamiltonian mechanics, so we can solve many problems in a very compact way. Okay, we kept with the describing a system, mechanical system, in terms of the generalized coordinates, and as the last step, we apply this method for actual problem. Consider a particle sliding down a cylindrical surface where the cylinder is horizontal, that is perpendicular to the gravitational field, and this is the cross-sectional area of the cylinder. And this object begins on top of the cylinder and slide down without initial velocity. And at some point, because there is no friction at all, it departs the surface and make a free fall. If I make use of general physics, what I have to do is just analyze the force. mg is the gravitational force, and because it is sliding down the surface, there is a constraint force that is called the normal force. And at the end of the day, we'll find that angle theta is the arc cosine of 2/3. The constraint that the particle is sliding down on the surface of a cylindrical surface of a radius a, there is a constraint, r equals a. That means r minus a equals 0, and we might want to apply the Lagrange's undetermined multiplier method. The kinetic energy in this cylindrical coordinate system is 1/2 m r dot squared plus r squared theta dot squared. Potential energy of the system, this is a height from the floor, and this a cosine theta. And if I make use of this Lagrange undetermined multiplier, let me just say it is not fixed to be a, but in general we used mgr cosine theta. You know, this mg is the gravitational force, and radial projection is cosine theta, and the direction is opposite to the radial direction. So the Lagrangian is now written in this form with Lagrange's undetermined multiplier lambda multiplied by the constraint r minus a. The conjugate momentum for PR is mr dot, derivative of L with respect to r dot, and p theta is the angular momentum along the theta direction. Lagrangian can be differentiated with respect to r. There's a mr theta dot squared, and r depends on mr cosine theta, so mg cosine theta minus sine, and constraint force can be obtained from the derivative of r. This is just one, so lambda is here. You know, this mg cosine theta is mg is downward, mg cosine theta radial direction, minus sign means it is negative direction. But the normal force is along this direction, so this lambda represents the normal force. And mr omega squared style, this is the centrifugal force, that is fictitious force depending on the curvilinear system. This one is just, these two are conjugate momenta, and theta derivative of this comes from the potential energy. As cosine theta becomes minus sine theta, so negative sign is considered to have positive sign on it. Corresponding Euler-Lagrange equation of motion is given in here. Now, this is this one. The conjugate momentum is mr dot, and its time derivative mr double dot. And we have centrifugal force, gravitational force of the radial component, and normal force. And theta dependent term contribution is angular momentum time derivative. Where is it? This is the torque for the angular acceleration. Now we have two equations, but we have three unknowns, r, theta, and lambda. Now we bring in this constraint equation, r minus a equals 0. So we have three equations, and the problem can be solved. If we substitute r equals a, this one vanishes, and only these three pieces survive. So the normal force, the constraint force lambda, is mg cosine theta minus ma theta squared, because we have substituted r equals a. Again, if we substitute this constraint equation, some constraint condition, into the angular equation, we find ma squared theta double dot and mg a equals a sine theta. We observe that sine theta is positive all along this region. There's 0 degree to 90 degrees. Sine theta is a positive definite, so angular acceleration is always positive. So there must be a point at which this one, this normal force vanishes, increase, and this one decrease and increase. At some point they match to have this constraint force lambda cancel. So let us see. The system has the Lagrangian, which is independent of explicit time dependence. So Lagrangian has a partial derivative of time to be 0. And as we know, the second form of Euler-Lagrange equation states that the Hamiltonian is conserved. The total time derivative of Hamiltonian is a minus partial time derivative of Lagrangian is the second form of the Euler-Lagrange equation. And Hamiltonian is given by the velocity, the time derivative of coordinate multiplied by conjugate momentum summed over the whole cases. If we substitute the conjugate momentum in here, we find that this one and this one gives again the kinetic energy term. And if we want to write down the Hamiltonian in a conventional way, r dot and theta dot must be replaced with the conjugate momenta instead of time derivative of coordinates. So if we substitute that and the potential energy is flipped, the sign of the potential energy is flipped, So this is the total mechanical energy of the system. We remember that second form of Euler-Lagrange equation states that this Hamiltonian is always conserved. The initial value at theta equals 0 is vanishing kinetic energy, so vanishing angular velocity. That thus we have MGA. Now, this condition gives theta dot squared is 1 minus cosine theta multiplied by a cancels, and this factor of 2 appears in the numerator, 2g over a, 1 minus cosine theta. Again, our angular equation was that theta dot squared equals g over a cosine theta. This time derivative, this angular velocity square in this angular equation, time derivative scale obtained in the Hamiltonian must be the same. So we have this g over a cancel, and cosine theta equals 2 minus 2 cosine. Therefore, the 3 cosine theta equals 2, and cosine theta is 2/3. Now, we consider the generalized coordinates for two-body system. This two-body system analysis is very important in any kind of classical mechanics, and even in quantum mechanics. If we consider the particles' position to be x1 and x2, and their masses m1 and m2, what we find is that the center mass, which is defined by m1x1 plus m2x2 divided by the total mass, must be on the straight line that connects the two particles. We remember this is xcm, center of mass position, and let us use just capital X, because of cm, writing the subscript cm everywhere is just too busy. Let us consider the displacement from the center of mass to the particle 1, that is x1 minus capital X. The displacement from the center of mass to particle 2 is x2 minus capital X. Now we define reduced mass. Reduced mass appears in any two-body system. For example, in the Atwood machine problem, we obtained the mass dimension term, which has the factor of mu. Mu is the product of mass divided by sum of the masses. And if we take the reciprocal of the both sides, then inverse of the reduced mass is the sum of inverse of two masses. Consider if we, at the end of the day, we will find that the total kinetic energy of the system is the kinetic energy of the center of a particle concentrated at the center of mass plus relative kinetic energy. That relative kinetic energy is expressed in this term. Here, this point like, if it were two particles at a single point, that this one will disappear. If it is not, we have additional piece. And this all appears always for any cases. So let us first simplify this displacement. Review displacement from the center of mass to the particle 1 is x1 minus x. Displacement from the center of mass to particle 2 is x2 minus capital X. This x1 minus capital X displacement from the center of mass to particle 1 is x1 minus this one. If we combine the denominators, then m1 plus m2 appears in the denominator. Numerator side, this m1 cancels the m1 vector, and m2 vector appears in front of x1. And both of them has the vector of m2. Again, x2 minus x has a vector of m1 instead of m2. The reason is that the distance from the center of mass here 1, here 2. The distance ratio is inverse m2 m1. Okay, if it is very massive, then this distance is longer. If it is the massive, this distance is longer. So this is reversed. So distance from the center of mass to particle 1 is proportional to mass m2. Distance from the center of mass to particle 2 is proportional to the mass m1. If we multiply m1 here and m2 here, and all of the vectors will be the same. So let us multiply m1 here and m2 here. Then if I multiply m1 here, and this one appears, these two are reduced mass. And we record that the displacement from the particle 2 to particle 1 is the relative coordinate r. This relative coordinate r is quite important in the analysis of the hydrogen atom problem. Therefore, if I move this center of mass contribution to the right hand side, I have this kind of form. If I take the derivative of both sides, first, if I add both sides up, then it is trivial to cancel, and this will result in the definition of a center of mass. Right? And if I take the derivative with respect to time, what I obtain will be the linear momentum of first particle and linear momentum of second particle is m1 velocity of the cm, m2 velocity of the cm, and plus mu velocity of the relative coordinate minus velocity of the relative coordinate. So this relation will be quite useful. Alright, so let us compute this, the kinetic energy of the two particles. So 1/2 m1 x1 dot squared plus 1/2 m2 x2 dot squared. So I would use 2m1 x1 dot squared 2m2 x2 dot squared. Okay, so if I substitute this one in here, so this square term This one is M1 and M2. That is the last term this one is we know that reciprocal. This is mu. This one is this. Therefore, it's mu x dot squared. Finally, the last term, the cross term, 2 times. So m1 mu and here 2 times mu here times minus 1. So they cancel. Therefore, the final result is alright. So the kinetic energy of the two-body system can be decomposed into kinetic energy of the center of mass at which all of the particles are concentrated at that point, and the relative kinetic energy. In the rigid body case, it has only the angular direction, but in general, the radial direction component also survives in general. By making use of this, we can construct a Lagrangian in terms of these new generalized coordinates. And please remember, x, relative coordinate x, is not the distance from the center of mass to a particle, but the distance between the displacement between the two particles. This is very, very important. And the relative coordinate has the conjugate momentum, mu xi dot, and total linear momentum can be obtained by taking the partial derivative with respect to the capital X dot. That is the conjugate momentum for the coordinate capital X. Okay, we can make use of this approach to consider the problem that is related to the connected two masses connected by a spring. This is again a central force problem in which the angular momentum is conserved, and as long as the angular momentum is conserved, we can describe this system in a plane. So if it is the case, we can write it down in the two-dimensional polar coordinate system, which is equivalent to the cylindrical coordinate system, as we just have derived the kinetic energy of the system is actually the sum of 1/2 capital M capital X dot squared plus 1/2 mu reduced mass. Mu is the reduced mass. Reduced mass also have the condition and you must remember relative coordinate x is the difference between x x1 and x2. So applying this one, the spring force contribution will give 1/2 kx squared. Okay. And that is radial part only 1/2 kr squared. So as a result, we can substitute this one. This Lagrangian must be negative sign there. And using this one, we can solve the problem in a straightforward way. And as you know, the angle dependence does not appear in the Lagrangian. Orbital angular momentum contribution is a conserved quantity, and the only problem, the non-trivial problem, is the radial component, and this is the answer. That's it.